a human information processing theory of the interpretation of visualizations, demonstrating its utility. The authors are Peter Cheng, me, Grecia Garcia, Daniel Raggi, and Mateja Jamnik. Human information processing is used in the title, but for short I will use the term cognitive throughout the talk. To provide some motivation, consider these pairs of representations, which better supports access to the information or making inferences or solving problems. Why are some of these better than others? In fact, each of these pairs of representations have been empirically tested, and it's the upper one in each case that was found to be superior. Clearly, it would be useful to be able to quickly evaluate theoretically the relative efficacy of alternative visualizations. Also, it would be good if we could have explanations of what makes a representation effective that's grounded in cognitive theory. This paper concerns an approach that enables the easy assessment of alternative representations by building cognitive models. The cognitive models are of the informational structures that users build in their minds whilst they are using visualizations. This talk has two parts. Firstly, in previous work we have created an approach to the cognitive modeling of representations, and the first part of the talk will give an outline of that approach. It has three components: representational interpretive structure theory, and that's operationalized in a graphical modeling notation, RIST. The kinds of models built look like this. They're network structures. We provide a browser-based editor for the convenient construction of such models. The second part of the paper concerns evaluation. So far, the research team has built many models of different classes of visualizations as a way to test the approach. However, something a bit more formal is really required. To introduce the approach, let's consider the theoretical requirements of RIST and also how it is operationalized in RIST. The theory is a cognitive one, so we want it to be consistent with cognitive theory in general, and we do so by adopting an established account of the nature of memory structures, namely the idea of schemas. The theory proposes four types of schemas which perform different representational functions. They have different shaped icons in the modeling notation. The theory makes a strong cognitive claim that the overall purpose of the mental representations of a representation is to closely associate information about the represented world with components of the representing world. In other words, the concepts being used and the graphical objects of a display. These are captured in the schemas. In the notation, the names of concepts are at the top of each of the icons, and the graphic objects are indicated at the bottom. A model of an interpretation is a network of such schemas. It has a hierarchical structure, and meaning is inherited downwards throughout the network. So the RIST notation has syntactic rules for maintaining the correct hierarchical structure of the schemas, and the editor in fact includes routines to ensure that only syntactically correct models can be built. We want the models to be interpretable with respect to established theories of representations. So the schemas encode information about properties of concepts and properties of graphic objects. For example, the nature of quantity scales is considered to be important in many theories of representations, and so these are encoded in the schemas and represented in the notation To make all this a bit more concrete, here is a collection of digital clock displays. Each has an overall interpretation consisting of a specific month, day, hours, and minutes. Here is a model of this display. All four types of schemas are present. The representation schema is lozenge-shaped, and it signifies the entirety of a representation. At the bottom level in a model, we have R symbols. These are rounded rectangles. What they do is to pair one specific concept, such as a value, a fact, with one graphic object. The trapeziums are R dimensions. An R dimension is a class or a variable, and it will be associated with different instances of values. The graphic objects of R dimensions include things such as graph axes, ranges of colors, or alphanumeric labels. This schema encodes quantity scales of both the concept and graphic objects. The final class of schemas are R-schemes, which is a plain rectangle. These are complex conceptual structures and are associated with complex graphical structures. The overall hierarchy of the network is established by the connections between schemas. Reading downwards in the diagram, we have predicates such as value of, has property, or has part. We have built models for many and varied types of visualizations and representations. An interesting discovery that we've made in our previous work is the existence of subnetworks that are common across diverse forms of representations. These we call idioms. As an example, one type of idiom in this model are one type of coordinate system. Here, a date is coordinated out of a month and a day. There's another coordinate system combining hours and minutes to give an overall time, and a higher level coordinate system which combines the date and the time to give the overall display. That's a quick overview of our approach to building cognitive models of visualizations. The second part of the talk is about evaluation, and there are three aspects to assessing our theory. First, we're going to compare the predictions of the models to assessments of the efficacy of representations determined empirically. Second, we can look at the explanations that are derived from the models and see whether or not they are consistent with prior explanations. And we can also see whether the models provide new cognitive insights. As the models are models of memory structures, not models of actual information processing, we cannot yet obtain absolute predictions of performance. So our strategy is to compare alternative representations which in the literature have been determined one to be superior to another. We then build models of each one of these, and we can inspect the models in order to try and come up with explanations about the relative efficacy, and also we can make quantitative predictions about their relative efficacy. And if the order of the prediction of which one is superior compared to the other matches that of the empirical studies, we have some evidence for the adequacy of our approach. So what are the kinds of criteria that we can use for quantitative evaluation? Let's have a base model, which we're going to compare with various target models. We can identify various criteria. A model of a base visualization is going to be cognitively superior than a target visualization when the target model meets some or all of these criteria. This comparison is done on a basis that the visualizations must be informationally equivalent and on a everything else being equal basis. Let's consider each one of these criteria in turn. The first one, when a target model has more schemas than a base model, the base model is likely to be better. The second criteria, when a target model is more branchy than the base model is likely to be better. Third criteria, when the target model is deeper than the base model the base model is likely to be superior. The fourth criteria, when the target model has more complex links than the base model, the base is likely to be better. The fifth criteria, the target model, which is more heterogeneous than the base model, will likely mean that the base model will be better. And the sixth criteria concerns quantity scales and whether they are compatible between the concept and the graphic for each of the R schemas. These are the pairs of representations from the empirical studies that we've considered and built models of. In each case, the model at the top is the one which was found to be superior in the empirical studies. Let's start with the Sankey and chord diagrams. Gutwin in 2003 presented a study in which Sankey diagrams were shown to be superior to chord diagrams across many performance measures. These are the two models that we've built of the memory structures that would be associated with these two representations. On first sight, they're comparable, but the chord model actually includes many placeholders for information that's actually repeated across many structures. When we quantify the two models according to the criteria, is better in the Sankey diagram compared to the chord diagram. The second case study we did was based on Larkin and Simon's seminal work, in which they demonstrated the superiority of diagrammatic representations compared with sentential representations. These are the models. It's clear that the model for the sentential representations are clearly much more cluttered, but again, some of the detail of the model has been omitted, this time just for the sake of readability. Quantifying these in terms of the criteria, we again see that the pulley diagram is superior on almost all of the criteria compared with the sentential representation. The story is similar for alternative line graphs as studied by Peebles and Cheng in 2003. Again, according to the scores on the criteria, the empirically superior representation, the phase plot, is predicted to be better than the function graph. The final example is that of electricity representations, in which conventional representations for electricity, which include algebraic equations and a circuit diagram, were compared with a novel graphical modeling diagrams for electric circuits called AVAL diagrams. And again, the same picture emerges. So overall, when we look at all of the cases, the predictions made from comparing the models are always consistent with the empirically derived findings. So to round up, why should we build cognitive models of interpretations of visualizations? Well, it's a way to theoretically assess the relative efficacy of alternative visualizations in a way that's relatively quick. Also, the models can provide some insights in terms of cognitive explanations of the predicted differences between visualizations. We've provided an approach to do this in the form of a theory which is operationalized in a graphical modeling notation, and we give a browser-based editor for the easy construction of such models. This paper has specifically shown the potential utility of the approach and also provides a first initial demonstration of the validity. Although we didn't consider this in particular detail in this talk, the models also provide novel cognitive explanations for the performance of alternative representations. This was a preliminary evaluation, so further empirical studies with actual users are required. Thank you for your attention.